This episode of CppCast is sponsored by Undo Software. Debugging C++ is hard, which is why Undo Software's technology is proven to reduce debugging time by up to 2/3. Memory corruptions, resource leaks, race conditions, and logic errors can now be fixed quickly and easily. So visit undo-software.com to find out how its next-generation debugging technology can help you find and fix your bugs in minutes, not weeks. Episode 41 of CppCast with guest Mark Logan, recorded January 14th, 2016. In this episode, we talk about building static analyzers in Clang. Then we'll talk to Mark Logan from Artillery. Mark will talk to us about his experience building a game engine in JavaScript and C++. Welcome to episode 41 of CppCast, the only podcast for C++ developers by C++ developers. I'm your host, Rob Irving, joined by my co-host, Jason Turner. Jason, how you doing tonight?
Doing all right, Rob. How about you?
Doing pretty good. As I was just telling you, the next few weeks might be a bit hectic for the show. I'm doing a business trip, and I'm also going to be moving again, as I think I mentioned to you before, but I haven't brought up on the show yet. It shouldn't be as much of a move. I'm just moving across town, basically, but still have to do a lot of packing, and it might interrupt the show a little bit. So apologies ahead of time to all listeners if we miss a week or two, but I just want to let you all know.
You know, it really doesn't matter how far you move. You still have to pack everything you own and then unpack it again.
Yeah, so that part just takes some time. Anyway, at the top of every episode, I'd like to read a piece of feedback. This week, Matt writes in about last week's episode, and he just wanted to say how glad he was to run across the podcast a few months ago. He really enjoys C++, and your guest discussions have been really good. The more technical, the better. He's very biased towards the Unix and Linux platform as a C++ development environment because he's been working on it since the 80s. So it was nice to hear that UndoDB was geared towards developers like him. And he hopes we continue to include Linux as at least an equal peer to Windows. For him personally, that's one of the best aspects of your podcast. So many other programming podcasts focus on Windows or Mac development environments exclusively, so yours is unique in that way. I've tried really hard to make sure we're balancing Windows and Unix specific topics because I think that's representative of the C++ community. What'd you say, Jason?
Yeah, I almost feel like there's maybe more Unix C++ developers than Windows, but that could just be a complete fabrication.
I don't know if anyone's done a study on the numbers. I remember way back when we did a poll asking about development IDEs, what people are using. And I know Visual Studio was up there. So
right.
Just based on that alone, you think there are a fair amount of Windows developers for C++.
Yeah, I'm sure that's true.
Yeah. Anyway, thanks for writing in, Matt. We'll definitely keep Linux topics in the show. Don't have to worry about that. And we'd love to hear your thoughts about the show as well. You can always reach out to us on Facebook, Twitter, or you can email us at feedback@cppcast.com. And don't forget to leave us reviews on iTunes. Joining us tonight is Mark Logan. Mark started learning C++ with Borland Turbo C++ back in high school so that he could build video games. After 20 years, he's finally starting to feel like he knows what he's doing. After graduating from Northeastern University's College of Computer Science, Mark spent 7 years at Google, mainly working on internal infrastructure and automation. And more recently, he returned to his first love, game programming, and helps found a studio called Artillery. He's currently the tech lead on Artillery's free-to-play RTS, codenamed Atlas. He spends his time working on performance optimization, networking, and solving cross-platform development problems. Mark, welcome to the show.
Thanks, guys. Glad to be here.
So a lot of people got their start on the Borland tools. I personally kind of missed those, but I love cross-platform development problems myself. Do you have any exciting anecdotes that you would like to share?
I have several that are I don't know, super technical and it might be a bit of a digression to start the episode off with.
Yeah, that's cool.
I think the most interesting thing I've had to deal with recently. So I guess we're going to be talking about C++ and JavaScript today. And the biggest cross-platform issue I've run into there is basically interoperating C++ and JavaScript on Windows. The stack frames become undecodable because V8, which is the JIT that we use, uses its own calling conventions that Windows stack walking code doesn't know how to deal with. So that's been kind of a ongoing tax on our own development. But yeah,
that does sound terribly exciting. Maybe we can dig into that in a little bit later here.
Yeah, sure.
All right.
Okay. Before we get to that, though, let's just go over a couple news articles real quick. And Mark, feel free to chime in on any of these. The first one is a new version of CPPCheck. Jason, did you want to talk about this one?
Yeah, anyone who's been paying attention to and stuff that I talk about, I guess, is I love static analysis tools and using all the tools you possibly can for your project. And so just, there's nothing terribly notable, I don't think, about this particular CPPCheck release, but I just wanted to let the world know, yes, CPPCheck is still in development, and you should use it.
And it's completely free, open source static analysis tool, right?
Yes.
Yeah, I think you talked about this on our very first episode together when I had you on as a guest, and you talked about how it was one of the better free GUI analysis tools, right? Or analysis tools that came with a GUI.
Yeah, it comes with a GUI, and it comes with Visual Studio integration if you want to work that way, or it also works great from the command line on Linux and Mac OS.
Very cool. So kind of building on that, if you want to go and build your own static analysis, there's this great blog entry going over how you can go about making that in Clang. And I don't think I've seen such a in-depth article really going through how to use Clang in order to build your own static analysis tool. It's definitely something we've discussed a couple times on the show, though, right, Jason?
Yeah, and it looks like potentially a great primer for getting you started with libclang with C++. The only other decent tutorial I've seen was using Python with libclang.
Oh, okay. Mark,
that sounds really... Oh, sorry, go ahead.
No, I was just going to ask you if you wanted to bring anything to the conversation.
Oh, I did read the post about building a static analyzer with Clang. I'm going to have to look into it more, because the thing I've always heard about Clang is that it's built basically to make it easier to develop tools on top of it.
Yeah.
Easier to write your own extensions to the compiler. But I've never had a chance to do that or seen a lot of really good intros on how to do that. So it seems pretty interesting.
Yeah, well, this article definitely provides that entry point if you want to get started with seeing the power of Clang as a library and analysis tool.
Yeah.
Okay, and this last one, this is actually an older article, but I don't think we mentioned it before, coming from the Visual C++ blog. And they're just highlighting that in the newest release of Visual Studio 2015, they added support for Incredibuild, which was a paid-for tool, separate from anything Microsoft provided. And they're now including it, bundling it in with versions of Visual Studio 2015. Which is pretty cool. And what Incredibuild does, if you haven't heard of it, is if you have multiple machines in with your coworkers, and you all have Visual Studio installed, you all have this Incredibuild package installed, then when you go to build, you can parallelize the compilation across multiple machines and get done significantly faster.
I think
that sounds. I'm sorry.
No, go ahead. No, go ahead, Mark.
That sounds really interesting to me. Compile times are sort of the big, one of the big downsides of C++. One thing I'd really like to see is a good compiler cache for Windows on C++. If you guys know of one, or if any listeners know of one, I'd love to hear about it. I've been looking recently, and
I have looked also and have not found one.
Yeah, it's kind of crazy that it doesn't exist, but.
Yeah. Well, I think Incredibuild provides part of that, but I'm also a little confused as to exactly what is free. It seems like it's just the standalone single host instance of Incredibuild that is free, which still gives you a good performance improvement because it can better parallelize on your local box.
Oh, is that what it is? Okay, so it's kind of just an entry into it. They're not giving you everything because, yeah, I think if you buy IncrediBuild from the company, you can, install it on as many machines as you buy licenses for, and then all those machines can kind of just, you can take advantage of their processors to improve your builds.
And it does work well. I do know I have a client that is using it, and they get good use out of it.
Very cool. Okay, well, Mark, we have you on here, and as you mentioned, we're probably going to be talking about some C++ and JavaScript. Let's get started with just tell us a little bit about what you're developing with at Artillery.
Sure. So we started out a couple of years ago trying to build a pure JavaScript game engine, and went quite a ways with that, and eventually determined that JavaScript, at least native idiomatic JavaScript, was not going to be fast enough. And so we started taking sort of an incremental series of steps, getting into C++ more and more. And the first part of that was basically using Scriptum to compile C++ into JavaScript in the form of asm.js, which is a restricted subset of JavaScript. And doing that got us massive speed ups. And at this point, basically what we have is a game engine that runs in the browser and as a native application. And this is all accomplished through either compiling JavaScript or compiling C++ into JavaScript and running into the browser, or we have essentially a native port of the engine that embeds V8 and runs the C++ code natively, and then calls back to JavaScript in order to run the JavaScript parts of the game. So it's been a kind of a pragmatic process, and I think what's interesting about it is we've come at things somewhat in the opposite direction from a lot of game studios, where typically they'll start out developing in pure C++ and then add a scripting language, often Lua or something like that, or their own in-house scripting language. We sort of started with a scripting language and then later started putting C++ into it and arrived at a somewhat similar place in the end.
Right.
So you said that C++ compiled to asm.js was actually faster than the equivalent native, if you will, JavaScript?
Yes, it's far, far faster.
Interesting.
There's a couple reasons for that. Probably the most important is that if you're just writing idiomatic JavaScript, there's very little you can do to get cache coherency. Because if you're using an array, a native JavaScript array, you don't even necessarily know that it's contiguous. I'm sure in general it is, but the individual elements in it are probably going to be boxed numbers. So really, every element in the array is going to be a pointer to somewhere else. And then if you have an array of objects, it's even worse. If you are writing C++ and you are controlling your memory layout and you have just a big array of structs that you need to iterate through, that all gets compiled into JavaScript, but the JavaScript it ends up looking a lot like assembly. And so really you just have this essentially the heap in JavaScript is just a big typed array. For people not familiar with JavaScript, the typed array is basically an abstraction onto sort of raw memory that exists in most modern JavaScript VMs. And then you can have your C++ code executing in JavaScript, and all it's really doing is accessing contiguous elements in this array, just like you would be accessing contiguous addresses in memory if it had been compiled to native code.
Interesting.
Yeah, so that's I think the biggest reason, at least on modern processors, where cache coherency is so important. The other thing is that when you compile C++ to JavaScript, the JavaScript that you end up with it can be type monomorphic. You never have to worry if you have a function that gets called in asm.js from and it was produced from C++ code, then you're never going to get a different type for one of the parameters of those functions because the type checker in C++ has already verified that that's not happening. And so once you're doing that, it basically means that a lot of the dynamic nature of JavaScript is gone. And different JavaScript VMs take different approaches to this. Firefox's VM called SpiderMonkey we'll actually take the asm.js and just blast out native code from it. So it just recompiles the asm.js to native code. V8 doesn't do that, but V8 is very heavily JIT-based language, and it's going to have a much easier time optimizing the code when it's type monomorphic, because it can say, okay, the last 20 times this function ran, we got an int for this parameter, and we got a float for the second parameter, and whatever. And then it can produce optimized code for that, and it will never have to bail out of that optimization, because it's never going to get a call to that function that violates the measurements that it had already taken that guided the JIT optimization process.
Okay.
Does that make sense?
Yes.
Okay.
At the risk of immediately diving into the weeds here, I'm curious what kind of performance differences we're talking about. If you have just, ballpark numbers like idiomatic JavaScript versus native C++ versus C++ compiled with Scriptum.
Sure. So ballpark, we've been kind of in this process of gradually rewriting different pieces of the engine in C++. And in general, what I found, so a lot of the code that we're rewriting is stuff that just kind of has to do a very simple thing to a lot of different entities. So for example, I don't know if you guys play many RTSs like StarCraft, but typically you'll have a little mini map in the corner that shows the positions of all the units on the game map. And so that's just code that has to go through all the units, and it puts the position of the unit into a vertex buffer that gets uploaded to the GPU so that it can just be rendered as essentially a dot on this map. So all this code is doing is it's going through an array of things and then writing, an XY coordinate into a memory address. So when we move that code into C++, the sort of overall speed up was between 5 and 10x, and the marginal speed up, in other words, like the cost of adding one additional unit into that, disregarding the overhead, the marginal speed up was like 20x, just compiling to JavaScript. So it was hugely, hugely faster, and almost everything that we ported in this way, we just suddenly didn't have to worry about it anymore. It just became almost too small to measure.
Wow.
Which was really nice. And then we had more complicated systems like our renderer, which has to do a lot more interesting things, and it's not just sort of straight line, just blast through memory in sequential order. That was not as dramatic a sort of overall speed up, but it seems that the big benefits we get are sort of in the marginal, at the margins. You can just keep adding stuff and it doesn't change it very much. But we only got like a 2 or 3x speed up from where we started on that one. So in general, I would say, going from idiomatic JavaScript to C++ that's compiled back into JavaScript, you can somewhere between 5 and 20x depending on n. And then Scriptum asm.js is commonly measured to be like 1.5x to 2x slower than native C++ code. But that's kind of a moving target because V8 and SpiderMonkey, they just keep getting better and making things faster.
Right.
So
have you tested it against IE's new JavaScript engine that was just open sourced?
We have not.
Okay.
Been too busy for that.
Sure.
But sounds fun.
I'm just curious.
Yeah. We'll get to that if we can.
Yeah.
Just to pull it back a little bit, I had not heard of Project Atlas or Artillery much before going into this interview, but I just did a quick search and I found this interesting article, how Project Atlas could kill the console and change gaming forever. So this is a pretty serious game.
So that's that article.
Oh boy,
is that was written. Where was that again? Was that on
Daily Dot?
Daily
where I found it.
Okay.
Yeah.
So when you're fundraising, you tend to have a lot of these sort of somewhat more hyperbolic articles written. Yeah, I mean right now we're focused on making one fun game, and we'll get around to killing the console later, I guess.
It looks like, comparing it to StarCraft 2, though, is a pretty good comparison, just judging by the images I'm seeing on the internet. It looks like a pretty beautiful looking game, and it would be impressive to see this running in a browser.
So it is inspired in a lot of ways by StarCraft. It's one of our favorite games. Probably, I don't know what images you're looking at. There's some very old ones out there that we kind of cringe at when we look at now. But I'm sorry, was there? I think I lost my train of thought. Was there a question in there?
I'm not sure if there was really. So a question I did have, though, was when you first started and you were looking at JavaScript, were you aware of Scriptum at the time and you just chose to go with, just pure idiomatic JavaScript?
We were aware of it, but we didn't start out from day one building Atlas. We started out building some much simpler games that really had no need for the higher performance requirements.
Okay.
So once at a certain point, we decided to focus more on a much more ambitious game, and that was when it started to become necessary. So we had like one demo that was essentially, it was a clone of Bomberman, the old NES game, and we were trying to sort of position ourselves as providing tools and middleware for games on the web, and we pivoted away from that at a certain point.
Did you consider any other languages besides JavaScript at that time?
Since we were targeting the browser, no. Oh, I remembered what I was going to say. The game, in regards to your earlier comment, the game does run in the browser right now, and we use it a lot for internal development. We probably won't ship a playable version in the browser because there's some somewhat insurmountable sort of user experience problems in the browser, specifically like the escape key always takes you out of full screen, and there's nothing you can do about it. And so, but we probably will be shipping replay viewing and observing in the browser, which we're pretty excited about because we think it's something that hasn't been seen before in a web browser, for sure.
Okay. So
what does your overall architecture look like then? Do you have anything that is compiled to native code from C++, or are you?
Oh yeah, in our native, we're the game now. We mainly ship to playtesters as a native application, but it's the same engine that also works in the browser. And the basic architecture is that the code that in the browser would have been compiled to Scriptum, in the native application it gets compiled to native code, and we call it via the V8 C++ API instead of calling it as Scriptum code inside the same JavaScript VM. So from an application perspective, it looks more or less the same. Underneath, it's ASM.js in the browser or native code on the native clients.
So do you have like a lot of moving parts to manage to make that all work, or does it all kind of happen naturally?
I wouldn't say moving parts. Basically, when we started transitioning to the native platform, we basically had to build a binding generator. So Scriptum has a lot of different, or it has 3 different ways to generate C++ bindings that you can access from JavaScript. The one that we use is called the IDL binder, where you write your binding definitions in WebIDL. I don't know if you guys have seen IDL before.
I've seen IDL from a long time ago. Things called IDL.
Okay, so there's a subset of it called WebIDL, which I believe that the Chrome team uses to sort of generate their internal bindings, or maybe it's Mozilla uses it. For all the things that you use in the browser that are actually all the JavaScript APIs that browsers present that actually are implemented in native code.
Okay.
So Scriptum built a binder based on a binding generator based on the same IDL language, and so we started using that. And then when it came time to make the transition to a native application, we had all these binding definitions written. So we just wrote a binding generator that could generate V8 C++ bindings for our code, so that we could call into it from JavaScript.
Interesting. Did you try? Well, I was going to ask if you tried using Swig, but Swig doesn't give you the Scriptum side of it that you need. It only gives you the V8 side of it that you need.
Right, exactly. Yeah, and possibly we would have done that if we had gone in the reverse order. But since we started with Scriptum, we were already that was the world we were living in. And the binding generator, it turned out to not be a huge amount of work, since we were starting with a very clearly defined problem space. It's basically just provide the same functionality that Scriptum provides. So it just became a matter of writing a bunch of code to spit out C++.
Right.
Yeah. The unfortunate thing is that the size of the bindings becomes prohibitive once you have sort of not prohibitive, but it becomes inconvenient once you have a reasonably large application. So we have, I think, about 400 classes that are exposed.
400 classes.
Classes, structs, etc. And part of that is some of that is third-party software. But anyway, it's enough that our native binding generator spits out about 1.5 megabytes of C++, which takes a long time to compile, unfortunately.
Well, when I've played with Scriptum in the past and tried to compile heavily templated code, it doesn't necessarily like that. It seems like I'm, overwhelming the symbol table or something. I don't know. It seems to take a very long time. Last time I tried, but there's been large improvements every time that I've tried it, and it's been a while now. I was just wondering if you've hit any limitations with it or had any problems.
The one thing with Scriptum that is a bit of a bummer is that there's no incremental linking. Okay. So it's all built on top of Clang. So sort of the front end part of it compiles all your C++ files into LLVM bitcode, and then so that's all. It's a custom fork of Clang, but it's mostly just Clang. So you end up with all these bitcode files, and then the Scriptum linker turns those all into JavaScript, which is kind of an interesting process, because obviously JavaScript is not assembly or machine code, so you don't have jump instructions and branch instructions. So there's this process where they have to turn bitcode, LLVM bitcode back into JavaScript constructs like ifs and functions and things like that. So that takes a while. And then also in order to make so that they have all sort of the translation level unit optimizations all happen in LLVM. They get to take advantage of all that. But once it gets turned back into JavaScript, they have another pass that actually re-optimizes that JavaScript. And that part of it takes a while. So you end up with this link step, which is basically this non-incremental link for your whole project, and then an additional optimization pass over the output of that. I might have gotten some of the details wrong, but that's basically how it goes. And so you end up with essentially just a long linking step, even when you've only changed one file. So that is a bit of a bummer.
Is it prohibitively long? Does it mess with your development times?
It's probably, lately it's gotten up to maybe a minute sometimes. So it's inconvenient. It's not prohibitive. Okay. I'd love for it to be faster, but I'm, I try not to be too critical, given that the fact that Scriptum even exists at all is kind of a miracle. So.
I want to interrupt this discussion for just a moment to bring you a word from our sponsors. Do you spend half your programming time finding and fixing errors? Is printf your default go-to when you encounter a bug? At Undo Software, they know that debugging C++ can be hard. That is why their next-generation debugging technology for Linux and Android is designed for C++ users, and is proven to reduce your debugging time by up to 2/3. Harness the reversible debugging capabilities of UndoDB, the reversible debugger for Linux and Android, and step backwards as well as forwards to find the root cause of a bug. Use watch points to reverse continue straight to the time a variable was last changed. Memory corruptions, resource leaks, race conditions, and hard-to-find bugs can now be solved quickly and easily. Visit undo-software.com for more information and start fixing bugs in minutes, not weeks. One question I had is you're working on this game engine and you want other game developers to be using it, I'm assuming. Are they going to be working with a JavaScript API, or will they be able to work with it in C++ as well?
Right now, when we started, we were much more focused on building something for third-party developers. Mm-hmm. We came to the conclusion at a certain point that most platform companies get started by releasing a successful game.
Right.
Unity is the obvious exception, but other than that, there aren't a lot of really strong exceptions to that rule. So right now we're just very focused on building a fun game, and the kind of considerations about third-party development are not as important to us right now. I think if we do want to do that later on, after launching this game, it will involve pretty thorough redesign or rewrite of the engine. But I think if somebody were to just jump into the engine right now, it would be essentially a mix of the two. There's some things that you want to do with JavaScript, and there's very clear ways to do it. And then the C++ side of things kind of has its own set of abstractions that are oriented more around ensuring things like sequential memory access and cache coherency and all the things that you want to do in order to make your code really fast.
So does your does the interaction between C++ and JavaScript go both ways, or is it only the JavaScript side calling the C++ libraries?
It goes both ways. And the mechanism that we use to do that is you can, in the IDL binding generator, the Scriptum one, and then also the one that we built that sort of mimics it, you can define an interface which basically causes the binding generator to make an abstract make a subclass of an abstract class, and then you can provide implementations of the virtual methods in JavaScript.
Right.
And so you can pass in a pointer to your class that has these JavaScript virtual method implementations on it. You pass that in C++. C++ calls that code, so it can call some virtual method, and then that call goes back into the bindings, and the bindings dispatch the call back to JavaScript, and then you have a function in JavaScript that takes some arguments that have been suitably handled by the binding layer. So if you're just passing a number, you just get a number. If you're passing a C string into the virtual function, then you're going to get at least in Scriptum, you're going to get just a pointer as the argument, and then you have to call a special Scriptum method to turn that pointer into a string by reading it out of the heap. So it's a little finicky, but it works very well in practice, and it makes it quite easy to do most of the things that you typically want to do.
Well, it sounds like a great opportunity then to bring up the Windows problems that you mentioned right at the beginning of our talk.
Okay. Yeah, so that's been a fun one. Basically, I guess actually let me back up a bit and kind of talk about the challenges of debugging in an environment like this, because I think that's probably one of the biggest downsides.
I was just thinking about that.
Yeah, and this will tie into the stack issues. So if you're developing simply in Scriptum in the browser with C++ and JavaScript, it's not too bad, because if you put a breakpoint somewhere and then you look at your call stack at that breakpoint, the JavaScript functions will, of course, just look like JavaScript functions. The C++ functions, first of all, if you have optimizations on, things can get inlined. And obviously anybody who's using, GDB regularly is familiar with that. But you don't always expect to see that in a browser developer console. So that can be a little confusing. And you also need to be careful about what optimizations you turn on, because Scriptum will also run the closure compiler, which is basically a super powerful minifier for JavaScript, and it will replace all your functions with super short strings like ZN4 and, Q8 and things like that. So assuming you're not running into any of those issues, then you get a call stack that basically shows you exactly what's happening. And if you actually look at the C++ code, it's, and you want to step through it, it's not really any worse. And arguably it's probably even easier than reading, straight machine code assembly. The JavaScript that gets produced it looks a little bit like assembly because all the variables are like $0, $1, $2. So it's like, okay, well, I guess those are my registers, and and then your memory reads, instead of a read instruction, you have like heap U8 and then a array index. So it's fairly straightforward to follow, but certainly not nearly as good as actually looking at your source code as it executes. When you're doing native development is where it gets a little hairier, because now you have to choose, okay, am I going to look at as I'm debugging my code, am I going to use GDB, or am I going to use the V8 debugging, interface? So you can either debug your JavaScript, in which case all your native code just shows up in the call stack as, native. Like it just says native, and you can't find anything else about it. Or you can debug in GDB, in which case you'll see all your native code, assuming you have debugging symbols, of course. And then the JavaScript stack frames in between those just are memory addresses, because the JIT has just, it's spat some code into some location in memory and called it, but there's no way for GDB to figure out what that address is. I'm sure it would be possible to, obviously V8, which is, I've been saying V8 a lot. Obviously, it's not the only JavaScript engine, but it's the one that we use on our in our native builds. Somewhere inside V8 is the information about what function that actually is, but building the plugin or whatever to GDB that would be able to find that out is be an interesting project if anybody wanted to do that. And then, things get even worse on Windows, where if you are debugging in Visual Studio, if you put a breakpoint somewhere in your C++ code in Visual Studio and stop at that point, if you've been called from V8, once the stack reaches the point of being inside the V8 JIT, it just goes off the rails, because V8 uses a calling convention that's kind of like cdecl, but it's not really. And in any case, Visual Studio certainly doesn't know what to do with it. And so you get these stacks that just wander off into insanity. It'll say like 1,000 frames of the same function or whatever. So so that's probably the big the really one of the biggest drawbacks about doing things this way.
So that's only a problem when you're trying to debug from Visual Studio and inspect the memory between the interaction between the two.
Pretty much, yeah. It hasn't really hurt us too much in practice. We're able to debug most non-Windows specific issues on Mac as well, and there the calling conventions are similar enough that the debugger seems to have much less trouble most of the time.
Okay. So do you find yourself saying, choosing one debugging environment, the native versus the JavaScript, just because it's easier? Like, are you able to debug your issues, most of them in the JavaScript environment, for example?
So typically we still do a lot of our sort of day-to-day development purely in the browser.
Okay.
And so, 90% of the debugging that we're doing is just kind of everyday logic bugs where, something just isn't working the way it's supposed to in the game. And so you can go into the browser and pretty quickly zero in on it. The trouble is when we have platform-specific issues, like when we're, trying to figure out why some, GL call isn't doing what we wanted or something like that. And then you're stuck on the native platform. But even then, in practice, it hasn't been too bad, because we're typically looking at a pretty isolated piece of code. And so, the fact that the stack, the fact that you have 5 stack frames that make sense and then 1,000 frames of nonsense, in practice, if we're only looking at those, couple stack frames, it hasn't been too much of an issue.
Cool.
So, were you excited at your team about the WebAssembly news a few months ago?
I've been following that a little bit. I think as I understand it, the major benefit of that is basically increasing load times, because you have something that is a lot faster to parse for the browser than actually parsing JavaScript. And since what we're developing, we have a lot of asset loading basically anyway, so we have to load textures and meshes and all that stuff. So the actual parsing time of our ASM.js isn't all that bad anyway, compared to loading hundreds of megabytes of textures and meshes and things like that. So it's not a big pain point for us, but it does seem like, I think it's great that they're doing that. It's probably going to help a lot for smaller applications that aren't loading all this other stuff, and so that the parsing phase is much heavier for them, right?
This all sounds kind of magical. Like you can just compile your C++ to JavaScript land, and it's magically almost as fast as native code. And why does anyone even write anything in JavaScript at all anymore? I'm sitting here asking myself.
I mean, in a word, memory safety, I think would be the big one. If you like people always argue about, dynamic typing versus static typing and which one saves more time. And personally, I don't worry too much about that. I don't worry about anything until I have to deal with memory corruption. And then it's, it's like, it's your worst nightmare. And so, yeah, I wouldn't advise that anybody start writing web apps in C++ unless they have a real performance need to do that. Because it is a lot faster, but you do have to deal with all the C++ issues that we all deal with when we're just writing nothing but C++. But
right,
yeah.
Well, when do you project the game is going to be coming out if people are interested in looking into it?
So we've started doing limited external playtests. We had our first one in early December. We had about 1,000 people come in and test out the game. And basically over the course of this year, we're going to be doing a bunch of similar tests and growing each one with the goal to be in sort of a much wider beta by the end of the year. Possibly a limited, possibly public beta, but we're not totally sure.
Okay. Wow. And where can people find more information about Artillery and Atlas online?
Artillery.com.
Cool. And where can people find you online if they want to see more from your stuff?
I have a somewhat limited online presence. I was actually inspired to contact you guys after hearing, I forget what guest it was, but somebody was talking about dark matter developers. And I don't know if you guys remember that episode. So I said, hey, that sounds like me. But I do occasionally write blogs on the blog posts on the Artillery blog. I have a couple up there. We haven't had a lot of time for blogging lately because we've been pretty heads down. But
okay, great. Well, thank you so much for your time, Mark.
Thanks a lot, guys.
Thanks for joining us.
Thanks so much for listening as we chat about C++. I'd love to hear what you think of the podcast. Please let me know if we're discussing the stuff you're interested in, or if you have a suggestion for a topic, I'd love to hear that also. You can email all your thoughts to feedback@cppcast.com. I'd also appreciate if you can follow CppCast on Twitter and like CppCast on Facebook. And of course, you can find all that info and the show notes on the podcast website at CppCast.com. Theme music for this episode is provided by podcastthemes.com. at CppCast.com. Theme music for this episode is provided by podcastthemes.com.